All right, welcome to part two of energy. Now, at the last podcast, we were talking about how heat is transferred and everything, and then I ended up on mentioning, okay, what kind of temperature scales do we use? Well, just as a quick summary, uh, you know, if you recall what temperature is, and I don't know if we've defined it this year or not, but basically the simplest one is how hot or cold something is, right? Okay. So that's a real simple definition. Really, what it is a measure of is it's a measure of the average AVE kinetic energy, right? And that's the energy of particles moving, right? So that's really what's going on. Now in chemistry, we use a couple different scales. Um, And so I've got a slide here that shows you what they look like. Here they are. Now, in the gas law chapter we of course used the Kelvin scale. The rest of the world uses the Celsius scale. And of course in America, we use a Fahrenheit scale. All right? And so these are the three ones we use. Most of the time in science, we're doing this. Okay? Although, as you guys experience in gas laws, we had to use the Kelvin scale. Now, a Kelvin degree and a Celsius degree, as I mentioned before, they're the same. They're the same magnitude. However, they're off by this 237, which is why we added 237. We wanted to convert Celsius to Kelvin. Now, Fahrenheit's just all messed up. I mean, there's 180 degrees between the boiling point and the freezing point of water. Water freezes at 32, boils at 212. Just these numbers just make this scale ridiculous. Now, it doesn't seem ridiculous to us, of course, because we grew up with it. However, if you're someone in Europe and you grew up with a sunny day being 17 degrees Celsius, then it's not a big deal. But for us, Celsius seems really odd. So let's look at energy and temperature, because I got a couple things I want to show you. First of all, the transfer of heat does not always affect temperature. So again, if you remember last time, I talked about energy going from hot things to cold things, right? That's the way energy goes. But sometimes you can heat something up and the temperature doesn't change. And you're going, oh my goodness, how could that happen? Well, let me talk about this because this is really an interesting phenomenon. Let's say I'm going to heat up some water. And I'm going to draw a graph here. And this is, let's say, time down here. Oops. And this is temperature over here. Okay. Now, right here at this point, I'm going to add some energy. Let's just say times 0 and 100 just to make it easy. Okay. I'm going to add some energy to ice. And the ice is heating up, heating up, heating up, heating up. And let me write ice. I'll put ice in blue because that'll, of course, make it seem like ice, right? All right. So I've got some ice. And then all of a sudden, as you're heating up this ice, it gets to a point where it gets flat. All right? And we're not going to have time to do this in lab, but it's really a neat thing. And so my question to you is, what's going on? Why is this flat? And I would really like to draw that line a little better. Why is that line flat there? Okay? Well, maybe you know, maybe you don't know. But what's going on is right here, we start to get melting. Okay? And so what happens is even though I'm pumping in energy, okay? Even though I'm pumping in energy, the energy is not going into heating the substance. It's going to cause, it's going in the substance to cause the bonds between the water or the ice molecules to break up. And so after a certain point of time, then all of a sudden it goes like this. It starts going up again. Now, what do you suppose we have right here? Okay. Well, all of the water in my beaker is a liquid. And so it's heating up. Right? And then all of a sudden, after some time, it gets flat again. Right? Now, again, my question to you is, what do you think's going on? Why, even though I'm pumping it full of energy, is the temperature not going up? Well, maybe you're saying, duh, it's because right here, we're getting boiling. Okay, so then boiling's occurring. And then after all that water's gone, you could pump energy into steam, and you can heat up the steam. Okay, so right here we have steam. So it's kind of an interesting phenomenon. Whoa, stimp? I don't know what the heck that is. I know you guys are used to the way I spell this here. E-A-M. There we go. So it's kind of an interesting effect that even though you heat up some water, the temperature doesn't go up. And this is called a heating curve. And those of you that are going to spend some time with me next year are definitely going to get into that. All right. So let's look at a couple more things as far as energy, because this next quantity is a really very important thing, and that's called specific heat. Now, what specific heat is how much energy it takes to raise 1 gram of material 1 degree Celsius, right? And there's some real obvious everyday examples, but let me pull out a couple things. Oops. Oh. All right, so imagine this. I've got a substance here, and I'm going to add some energy to it. And as I add energy, the temperature is going to go up. Right? The temperature is going to go up. Well, what the specific heat is it tells you how much energy, and notice that's in joules. Joule is a unit of energy. What's an equivalent to joules in American units? How about a calorie? We know all about calories, right? How many calories? A calorie is a unit of measurement that we use in the U.S., but the rest of the world, they use joules and kilojoules. So it's how much energy in joules per gram per degree Celsius. And what I want you to notice here is look at the difference between the specific heat of iron and the specific heat of water. Look at those differences. They're 10 times, water is 10 times greater with 4.184 versus iron. Okay, so what does this mean? Well, that means if I pump in, let's say, 1 joule of energy. Oh, sorry about that. If I pump in 1 joule of energy, 1 gram of this substance will go up about 2 degrees. When I pump in 1 joule of energy into water, though, it's not going to change its temperature very much. And for proof of that, all you got to do is think about what would happen if you grabbed an iron bar, and held it in the Bunsen burner. Okay? Hold an iron bar in the Bunsen burner, what's going to happen? Well, within seconds, you're going to feel the heat, right? But now I'm going to have you hold a beaker in your hand over a Bunsen burner. How long is it going to take before you can't hold that beaker? It's going to take a while because water has a high specific heat. And it turns out that metals tend to have a low specific heat. That's what makes them great conductors of energy. I heat up a metal, it'll conduct that energy. And so they're good for use in pipes and heating applications like that, stoves, all those kinds of things. But what's really neat about all this is if you think about water, you can add a lot of energy to water and it won't raise in temperature too much, which is kind of a bummer when you're trying to boil water, because if you've ever watched water boil, it takes a long time. But it's nice because it keeps our planet at the nice temperature gradient that we have. I mean, think about the Puget Sound out here. It's pretty much in the 50s year-round. It doesn't matter if it's wintertime or summertime, that water is cold. Now, that's not to say the top layer doesn't get a little warmer in the summer, but it's still pretty cold. All right, and that's kind of what this bullet says right here. Water, the high specific heat means it can absorb a large amount of water. Now, these two values you have up here, the specific heat of iron and water, we can use that like a density. And so, whereas you could find out a mass and a volume of a substance and calculate its density and figure out what metal it was or what substance it was, we could do exactly the same thing with specific heat. And it turns out we're going to do that. So if I figure out how to find the specific heat of a material and I get a value that's like, like what we have up there, about 0.44 joules per gram degree Celsius, I can be pretty sure that substance is iron. And we're going to do a lab where we end up doing that. So specific heat is a real useful tool in identifying unknown materials. All right. On to the last slide. I've got a scenario here I want you to read. Pause the video for a second, and I want you to think about this and tell me if you could figure out which substance will have a higher temperature. Well, hopefully you guys all picked B. Oh, for crying out loud. All right, this may go down as the most interrupted podcast I've ever had. Anyways, did you pick B? Now, let me tell you why it's B. What does this number mean right here, this 0.325? It says if I pump in 0.325 joules of energy, I'll make 1 gram of substance B go up 1 degree Celsius. Whereas this one, I've got to pump in 6.5 joules of energy to get 1 gram of to go up 1 degree. So I've got to pump in more energy for A than for B to get it to go up in temperature. Now, because we're doing chemistry, we can always treat it with math, right? So let's do a little math and prove this, right? So let's do this. Let's say I take my 10 grams, right? I've got 10 grams of each substance. And I'm going to multiply those two. Why? Well, because look, grams is on the bottom, grams is on top. That gives me 6.50 joules per degree Celsius, right? All right. And then over here, I've got 3.25 joules per degree Celsius. So with my 10 grams, if I have 10 grams. Now, if we look up here, it says I'm going to pump in 100 joules. Oh, by the way, if some of you are screaming, yo, it says K up there, okay, well, that Kelvin and this Celsius, because they each of those is the same magnitude, it really doesn't matter if you see the book that says K or C. We still treat it the same. All right, so I've got these two values here, and I'm going to pump in 100 joules of energy, right? So I'm going to, as you guys know, if there's one thing we do here, we convert, right? 100 joules of energy times each. Now, I've got to flip this thing. Hopefully you would agree with me because you know how we like to cancel our units. 50 joules per degree Celsius, right? Per 1 degree Celsius. And that's 100, believe it or not. There we go. And so what do I get? I get 650 degrees Celsius. Whereas over here you could probably see that 100 joules times, whoa, sorry about that, complete brain fart. You guys are probably laughing at me. Let me take a second here and divide. Wow. Sorry about that. All right, how about this? Oh man, this is going to be 15.4 degrees Celsius. I thought that 650 was kind of big. And then this other one, 1 degree Celsius, 3.25. I don't know what this is going to be. This is going to be 30 something, right? So 100 divided by 3.25 equals, all right, so this one goes up 30.8 degrees Celsius, okay? So we've just kind of proved what you can kind of see by looking at this. This one takes less energy, only 3.25 joules, to cause 1 gram of the substance to go up 1 degree Celsius, whereas this one takes 650, all right? So there you have it, a little general review on, well, it's not a review, a little information on specific heat, and hope this video makes sense. Few interruptions, a couple brain farts by yours truly. So if you have questions on this, please feel free to ask me, and I'll see you guys later.